This lecture is on 11.3. There are 3 convergence tests that we'll study. Keep in mind we know about 2 series. We know that the geometric series converges for the absolute value of r less than 1, and we now have proven that the harmonic series diverges. In our convergence test, we will just see if a series converges. We won't find out what its limit is, and I hope that you all know by now the reason that we cannot find the limit in most cases is because down here I wrote we have no formula, no closed form for the general term of the sequence of partial sums. The first convergence test will be the comparison test. When we use it, we'll just call it CT, comparison test. If you have 2 positive term series, by the way, all 3 of our tests in this section will be used for positive termed or non-negative term series, where the a sub n's, b sub n's are positive. So the comparison test, we're given one series and we think of another to compare it to. And we have a relationship where, well, we have 2 series where a sub n is less than or equal to b sub n from some point on. So if you have this relationship here, a series where the a sub n's are under the b sub n's, then it won't surprise you that if sigma b sub n converges, then so does sigma a sub n. In other words, if the partial sums of sigma b sub n converge, then so do the partial sums of sigma a sub n. It's just exactly like the comparison test we had for sequences, because these are sequences really. It's saying that if a sub n is less than or equal to b sub n, then the partial sums of a sub n are all less than or equal to the partial sums of b sub n. In fact, that's how you prove this, just going back to sequences, but we're not going to do the proof. And if sigma a sub n, the series diverges, well, since the partial sums of b sub n are all above these, of course, so will sigma b sub n. Okay, so let's see how we use this. You look at your given a sub k here. Well, first you make sure it goes to 0, and it does. So this may converge. And you look at that and you think, well, what could I compare it to? Just kind of ignore, only look at the most powerful, what's controlling the denominator there, and it's 3 to the k. So a series that we could compare this to would be sigma 1 over 3 to the k, or 1/3 to the k, which we know converges, is geometric. So let's see, how would it compare? Well, this denominator, 3 to the k plus 1, is bigger than 3 to the k. So 1 over 3 to the k plus 1 is less than 1 over 3 to the k. So we have exactly what we want. We're given our a sub n is less than or equal to b sub n, and sigma 1 over 3 to the k converges. And you justify why you know that, and it's good enough to just say the absolute value of r is less than 1. That tells me you knew it's geometric and that r was 1/3. Okay, so a sub n is less than or equal to b sub n, and sigma b sub n converges, so I can just conclude, therefore, sigma 1 over 3 to the k plus 1 converges by CT, the comparison test. And notice when we're just talking about convergence, I don't worry whether it starts at 0 or 1 or 5. I just use sigma, because all we care about is whether it converges or not what the first 2 or 3 terms are. So we don't have to be quite as careful as we've been in 11 in 11.1 and 11.2 as far as where the sequence starts. Here's a second example. We'll use the comparison test. First of all, you see this series is sigma arctan. I like to get rid of those negative exponents right away, over 2 to the k. Now arctan, we know that the limit of arctan k as k goes to infinity is pi over 2. So all of these terms are a little bit beneath pi over 2 to the k. Oh, well, we know, let's say that I'm going to put the b sub n's in a different color. Let's compare it to then, this is what I'm thinking. I'm thinking that I'll compare this to pi over 2 over 2 to the k, which is geometric and converges. R would be 1/2. Pi over 2, this is pi over 2 times 1/2 to the k. So that's what I'd like to compare it to, and so let me show you how we would do it. Arctan k is less than pi over 2 for all k, and therefore arctan k divided by 2 to the k, that's a positive number, is less than pi over 2 over 2 to the k. And we know that sigma, I'm going to just write pi over 2 as a constant, times 1/2 to the k converges. You could put r equals 1/2, or you could put absolute value of r less than 1. Therefore, we have it. We have our a sub n less than b sub n and sigma b sub n converging. So we can say, therefore, sigma arctan k over 2 to the k converges by the comparison test. How about this series? Sigma 1 over the square root of n. Well, a sub n, it does go to 0, so it may converge. But I know that I'm thinking of I want to use a comparison test. I know that the harmonic series diverges. So I'm thinking, you know, this denominator is even less powerful than this one. So this is going to diverge too. But here's how we write it up using the comparison test. The square root of n is less than or equal to n for all n. Therefore, and it's positive, therefore I can take the reciprocals and get this relationship. And we know that the harmonic series diverges. We prove that. Therefore, we make our conclusion. Sigma 1 over the square root of n diverges by CT. So we got a sub n greater than or equal to b sub n and sigma b sub n diverging. Where I see students make a lot of mistakes in this is not putting the sigma in or using the word it. There's two sequences that we are talking about. These sequences here, these are the sequences of just terms in series. It is the sequence of partial sums that we're asking whether or not it converges or diverges. So be sure and say exactly what you think is converging or diverging. Are you talking about the sequence of terms that you're adding up, or are you talking about the series itself, which is the limit of the sequence of partial sums? Does that limit exist? Is asking, does it converge? The next convergence test is the integral test, and we'll call it IT, integral test. When we use it, you can just say IT for the integral test. Suppose that for all x greater than 1, the function a of x is continuous, positive, it's above the x-axis, and it is decreasing. And in fact, it'll look something like what you see on the drawing here. It will be decreasing and going towards 0. So then suppose that the terms of our series are a of k, a of 1, a of 2, a of 3. For example, if f of x was 1 over x, then a of k is the harmonic series, 1 over 1, 1 over 2, 1 over 3, etc. So the series sigma a sub k and the integral, the improper integral from 1 to infinity, they either both converge or they both diverge. So this is how you can, this is how the proof would go down here. It's easy to see. Really nice, in fact, to see this. Here's our function a of x, drawn as a nice, smooth, continuous curve. But our terms of the series, a of 1 would be there. A of 2 would be the y value here. A of 3 is here. And these are the terms of the series that we're adding up. So you can see that our a sub i's do go to 0. But we can use this integral if we know whether the improper integral converges or not. We can get the convergence or divergence of the series. Let's see. Let me write right here because you can't see the bottom of this. Let's say that in this picture, the integral from 1 to infinity of a of x dx diverges. If a of x dx diverges, then look, the areas of the rectangles, they're each width 1. So the areas of the rectangles is the sum of those areas is the sum of the series. It's a of 1 times 1 plus a of 2 times 1 plus a of 3 times 1. So if the improper integral, the blue area, is not finite, then certainly the sums of the areas of the rectangles are not. So if this diverges, we can see that sigma a of n diverges. Now, if you look at these rectangles a little bit differently, see, we still have the same points, a of 1, but now I draw a rectangle to the left. It's like a right endpoint sum. But you don't need to think of it that way. Just think a of 1 times 1, that's the area of this rectangle. A of 2 times 1 is the area of this rectangle, etc. Now, if we look at it this way, if we look at our areas of the rectangles under the curve, I can say that if the integral from 1 to infinity of a of x dx converges, in other words, the area under the curve is finite, well, the area of the rectangles is less than that. So we can say this implies that this sigma a sub n, or a of n if you want, a of n converges. Okay, so the integral test is going to be useful if we can find the improper integral. Of course, then we've always got the problem of finding an antiderivative. But if the improper integral converges, so does the series. If it diverges, so does the series. So it's a useful test for us. So the integral test gives us another series, kind of like the geometric series, that we need to have firmly in mind because we will use it as comparison series. If you remember, about 2 lectures ago, we proved that the integral, let me change this to white, we proved that the integral from 1 to infinity of 1 over x to the p dx converges only for p less than 1, and of course positive. So let's put that p greater than 0. Oh, excuse me, p greater than 1. I'm so sorry. I don't want to do this over. For p greater than 1. Converges when p is greater than 1. And we showed that it diverged when p was, certainly when it was negative. When it was equal to 1, it diverged, and when it was less than 1. So only for p greater than 1 does the improper integral converge. And so we can just say right now that the p series converges when p is greater than 1 and diverges when p is less than or equal to 1. So this is called a p series. We already knew that sigma 1 over n diverged, and there p is equal to 1. We know now, like a series like this, 1 over n to the 1/3 is going to diverge. But if I have 1 over n cubed, it's going to converge. This converges, this diverges. And you can just say p equals 1/3, p equals 3. These are p series. So here's a problem that we can use the integral test with. We want to prove, or we want to see if this series converges, and it says to use the integral test. And on our next test, I will ask you to use the integral test. Because usually if you can use one of the others, you would prefer it. This is a lot of work to use the integral test. All right, well, so I want to start by writing the integral. The integral from, well, this case 2 to infinity, but you could put 1 to infinity. Oh, no, you couldn't. Natural log 1 is 0. So the integral from 2 to infinity of 1 over x times natural log x cubed dx is equal to, always use the definition, the limit as t approaches infinity. If you skip these steps, you end up making a mistake. The integral from 2 to t of, and now I'm going to write this as natural log x to the minus 3 times 1 over x dx, because I can see it's a simple u substitution, u to the minus 3 du. So I'll just integrate as is and write the limit as t approaches infinity of, integrating, I get minus a half times natural log x to the minus 2 evaluated from t to 2. I don't have a function of t yet, but I'll get one now. The limit as t approaches infinity of, you know what, let's bring that minus 1/2 all the way out here. We don't need to, let's put it right out there. Okay, so now it's going to be 1 over natural log t squared minus 1 over natural log 2 squared. And I know that 1 over natural log t squared, this, the only thing that involves t at all, is going to 0. So this is a finite limit. Now, I don't care what the limit is, because the limit's going to be minus 1/2. Well, I'll go ahead and write the limit, but this is not important. It's going to be minus 1/2 times minus, so it's plus 1 over 2 times natural log 2 squared. All that's important is that we did get a limit. And if you want, you don't have to calculate that. You can just write, you can just show me that you see what's going to 0, and therefore the limit itself is finite. All we care about is convergence. It does not tell us what the series converges to. So we get a finite limit, and I'll write my conclusion here in yellow. I'll say the series converges by the integral test, and I've shown the use of it right here. The integral converges, so the series converges. Another example, it says specifically use the integral test. So we could also use the comparison test here, but this is just for practice. So I'm going to look at the integral from 1 to infinity of natural log x over x dx. We know that this is a positive function. It is going towards 0 because it's a natural log over x. It's continuous, so it satisfies the requirements needed to use the integral test. So we say, well, this is the limit as t approaches infinity of the integral from 1 to t of, and I'm going to write natural log x times 1 over x dx u du. So that is the limit as t approaches infinity of integrating, that was u du, so it's going to be 1/2 times natural log x squared evaluated from t to 1, which will be, now we'll have a function of t. The limit as t approaches infinity of, and I'll bring the 1/2 out there again, we don't need to worry about that. Pull the constant out and we have natural log t squared minus natural log 1 squared is 0. And you know that this diverges to infinity. So we can just draw our conclusion. Therefore, sigma ln m over m diverges by the integral test. Okay, so let's look at this. What test what would you want to use? Well, you look at this and you think, well, it looks, the most powerful thing there is k cubed. So I'm thinking, could I compare this, use the comparison test, and use as my comparison series, sigma b sub n, just 1 over k cubed, which is a p series with p equals 3. So it does converge. So let's see if we could use that. Let's see. We know that k plus 1 cubed is greater than just k cubed, so that 1 over k plus 1 cubed is less than 1 over k cubed. And sigma 1 over k cubed converges. Now you have to tell me how you know that, and I would just write p equals 3. You see it's a p series and p is greater than 1. We conclude then that sigma 1 over k plus 1 cubed converges by the comparison test. We compared it to a p series. Usually when you're using the comparison test, you're going to compare it to a geometric series or a p series. Okay, this one gives us a hint. It says use the fact that the natural log of x is less than or equal to the square root of x. Now we've talked about that before, and you're welcome to use, excuse me. That was strange. I don't know how that happened. You're welcome to use this fact that we've talked about several times. Let me get some white here. You know that the natural log of x is the slow grower, and even the square root of x is above it. So we know that the natural log of n is less than or equal to the square root of n for all n greater than or equal to 1. And since those are both positive, we could square them and keep the inequality sign in the same direction. Square root of n squared is n. Oh, excuse me, that was squared. Okay, so then taking reciprocals, they're positive. 1 over that is now greater than or equal to 1 over n. The inequality sign changes direction. And this gives us, we say, and we know that for p equals 1, or the harmonic series, it diverges. You could just say this, or you could put p equals 1, thinking of it as a p series. Therefore, we draw our conclusion. Summation 1 over natural log n quantity squared diverges. And we'll just say P diverges by the comparison test, excuse me. In this example, I'm thinking of a P series, and I want to look at this a sub k here and what's really happening. Well, I can ignore the plus 1. The square root of k squared is k. So this is behaving like, very similar to, summation 1 over k squared. And I know that converges. P is equal to 2. So I want to try, at least, to compare this series to sigma 1 over k squared. And I want, well, I'm hoping that mine will be underneath it so that I can say that that the series converges. So let's see. K times the square root of 1 plus k squared is greater than k squared. And therefore, 1 over k times the square root of 1 plus k squared is, taking reciprocals because they're both positive, I get this relationship, and that's just what I wanted. So I will say, well, let's say this inequality and sigma 1 over k squared converges. P equals 2. Notice I get the inequality, so I get my a sub k underneath my b sub k, and sigma b sub k converges, therefore my series converges. So I'll say therefore sigma, I'm just going to put a sub k to save time. This one right here converges by the comparison test. Our third test for convergence is the ratio test. And again, it is for only positive termed series. Now this one is a little bit, it's very new, the idea, but what the ratio test does is it compares, it divides a term of the series by the one before it. And really what it does is it measures how fast the a sub k's are going to 0. So we're not going to prove it. Unfortunately, we don't have time. But suppose that you have a positive term series. In other words, you have a sigma a sub k, and a sub k is greater than 0 for all k, or from some point on. Okay, you want to take the limit as k approaches infinity of the k plus first term divided by the kth, the one before it. If the term divided by the one before it has a limit which is less than 1, then the series converges. If it has a limit that's greater than 1, then the series diverges. And if it has a limit that's equal to 1, the test didn't work. It doesn't mean anything. You have to try something else. So the best way to memorize this test is to just use it. It works especially well. Let me write a note to you here on this. It's really a good test, good when a sub k has has factors of k factorial. It works really well for factorials if they're factors of a sub k, or its numerator or denominator. Okay, so it also works nicely with exponentials because you get lots of canceling. So, but remember the word factorials. This is really when you have factors of the numerator or denominator that are expressed in factorials, the ratio test works great. So these are all positive terms, so we don't really need any absolute value. We'll do that later, I'm sorry. So let's just take a sub k plus 1 here and divide it by the term before it. In this case, a sub k plus 1 would be 10 to the k plus 1 power over k plus 1 factorial divided by a sub k is 10 to the k over k factorial, which is 10 to the k plus 1 over k plus 1 factorial, and invert and multiply by the fraction in the denominator, k factorial over 10 to the k. Oh, well look, 10 to the k plus 1 over 10 to the k. 10 to the k plus 1 is just 10 times 10 to the k, isn't it? So the 10 to the k's cancel, and k plus 1 factorial is k plus 1 times k factorial. So the k factorials cancel, and we get this is equal to simply 10 over k plus 1. And as k goes to infinity, we get a finite limit of 0, which of course is less than 1. So we took the limit of the k plus first term divided by the kth term. We got a finite limit that is less than 1. Therefore, the series converges. The series converges by, and we'll call it RT, the ratio test. Let's try this example. Summation n squared over 2n plus 1. This is factorial. I see the factorial, so by far it's not, we can't the most powerful thing is that factorial, so we're not going to be able to use a p-series or a geometric series to compare it to, and we certainly can't integrate because factorials are not continuous functions. So it looks like we are going to have to try the ratio test. So I'm going to take the n plus first term. So that would be n plus 1, adding 1 to n everywhere I see it, n plus 1 squared over, oh boy, this is going to be a hard one, 2 times n plus 1, 2 times n plus 1, plus 1, factorial. And now that's over this thing, but I'm going to invert and multiply. So I have 2n plus 1 factorial over n squared. Okay, so now I'm going to rewrite this, because n plus 1 squared over n squared is n plus 1 over n squared. So I'll simplify that. And then I have 2n plus 1 factorial over that thing. Well, that is 2n plus 3, isn't it? 2n plus 2 plus 1. So I'm going to write it a little bit differently. I'm going to write 2n plus 3 times 2n plus 2 times 2n plus 1. Oh, factorial. These are going to cancel. So here's what this is just squared, and I know that n, whoops, I wanted that in yellow. Whoopsie. I've really messed things up. Oh. Okay, so I know the n over n plus 1, that goes to 1. And the 2n plus 1 factorials cancel. So what I have here is 1 over 2n plus 3 times 2n plus 2. That denominator, this denominator is clearly going to infinity. This factor here is going to 1. And so I can say I know that the limit here is 0. Again, I got a finite limit less than 1, and I can say therefore the series converges by the ratio test. I'm going to show you one more example. if we were given sigma 4 over, let's say, m factorial plus 4 to the m. Okay, you see a factorial there, but this is not a candidate for the ratio test because the factorial is not a factor in the denominator. It's part of a sum, and you won't get canceling the way we did on the last example. Now that denominator is really powerful. You have both the factorial and 4 to the m. So let's use the comparison test, and let's compare it to let's compare it to this series. How about, 1/4 maybe? 1 over 4 to the m. And maybe not exactly that, but I think we could get something close to that. So let's see. M factorial plus 4 to the m is certainly much greater than just plain 4 to the m. So 1 over m factorial plus 4 to the m is less than 1 over 4 to the m. And I don't quite have what I want there, but I can just multiply by 4 on both sides, and I get 4 and 4 here. And that's equal to 1 over 4 to the m minus 1. And I can say, and I know that sigma 1 over 1/4, I could put m minus 1 or m, it doesn't matter, converges. And that's because r is less than 1, the absolute value of r. Or I could just say r equals 1/4. So my conclusion is, therefore, the series given converges by the comparison test, and we compared it to a geometric series. So I could do lots more examples, but I'll give you some to work on, and you can ask questions in class.